All right, so last time we finished 5.1. The idea was still about diagonalizability. So a matrix, we said that a matrix or a linear transformation is diagonalizable if there is a way in which the space V on which that transformation is defined has a basis consisting of eigenvectors, right? So we went through that last time, and we've seen what that would mean. A basis of eigenvectors would mean that the matrix of T in that basis would be a diagonal matrix, right? And those diagonal matrices turned out to be what we called eigenvalues for the transformation or for the matrix. So what we did last time was to actually figure out how to find the eigenvalues of a linear transformation or a matrix, and you find them by setting up the characteristic polynomial, right, the determinant of A minus T identity, where A is the matrix or is the matrix associated to the transformation in any basis you want, right? And we did prove that it doesn't matter which basis you choose for that. And then once you have the eigenvalues, you can find the eigenvectors by looking at the null space of T minus lambda identity, right? So that's exactly what we did last time. So now 5.2, we want to somehow develop a test to figure out when a transformation or a matrix is diagonalizable, right? So far we know how to find eigenvalues and eigenvectors, but we don't know when it would be the case that the matrix of T would be diagonal. So let's start by looking at this result here. So what this is saying is the following thing. So you have a linear operator. Remember that an operator is just a transformation from V to itself. And lambda 1 through lambda k are just a collection of distinct eigenvalues, right? So you can pick 2 of them or 3 of them or, I don't know, all of them, but they have to be distinct. And then Vi would be some corresponding eigenvector. So each Vi is an eigenvector corresponding to the eigenvalue lambda I. Well, if you take this collection into a set of eigenvectors, and it turns out that the set is linearly independent, right? So you pick k distinct eigenvalues, then you choose an eigenvector for each. You put those theoretically, I mean, it might seem that they have nothing to do with each other, or what is the connection? Well, it turns out that they have to form a linearly independent set. So let's see how that works. We're going to do induction on K, where K is the number of eigenvalues that you start with. So step 1, let's say that K is 1. That would be the smallest value that we can choose. So we're starting with a single eigenvalue lambda 1. And with a single eigenvector, that would form that set, the underlying set in the statement there by itself, right? So I want this set to be linearly independent. So when is a set containing a single vector linearly independent? If the vector is non-zero, right? My vector is an eigenvector, so by definition, it has to be non-zero, right? All right, so we're done, right? So step 1, a single eigenvalue will form that set that is independent. So 2, so now let's say that the theorem holds for k minus 1 distinct eigenvalues and the corresponding eigenvectors. So any k minus 1 distinct eigenvalues, the theorem would hold. So now I want to prove it for k. So let's say lambda 1 through lambda k would be distinct eigenvalues. Okay, and v1 through vk would be corresponding eigenvectors. Right, so the goal is to show that the set containing the vectors v1 through vk will be linearly independent. And how do we do that? We just start with a linear combination of the k vectors and set it equal to 0. Okay, so what we're going to do next is to apply the following transformation to both sides. T minus lambda k, the last eigenvalue, let's say, times identity. The identity operator from V2 itself. Both sides, right? So what happens? Well, on the right-hand side, I just get 0, right? Any transformation applied to the 0 vector gives you 0. So now what is t minus lambda k identity applied to this first vector here, a1, v1? No? Let me write it here. So t minus lambda k identity applied to a1, v1 is t of a1, v1 minus lambda k identity. Lambda k is just a scalar, right? So lambda k times identity of a1, v1. T is linear, so a1 goes out. And lambda k is just a number. I'm just going to pull it out. And then identity of anything gives you that anything. So lambda k, a1, v1. All right, but what is t of v1? Who is v1? v1 is an eigenvector, right, corresponding to the eigenvalue lambda 1, right? So t of v1 is, in fact, lambda 1 times v1, because that's what defines eigenvalues. a1, lambda 1, v1, minus a1, lambda k, v1. Basically, we get a1 times lambda 1 minus lambda k v1. So that's what we get by applying the transformation to the first vector here. When we apply it to the second, we're going to get a sub 2 times lambda 2 minus lambda k v2 okay, all the way to the last one. So what happens when we apply it to the last one? We get a k times lambda k minus lambda k, right? So it turns into 0. So I'll just put the one before that. And then on the right-hand side, we get 0. Okay. But what we got in the end, the purpose of doing all this is the following. We got that sum, which is in fact a linear combination of the vectors v1 through v sub k minus 1, right? So it is a linear combination of the first k minus 1 eigenvectors that corresponded to k minus 1 distinct eigenvalues, and that is something for which the theorem holds, right? We assume that for k minus 1 it holds. What does it mean that it holds? It means that they are linearly independent, right? Any k minus 1 eigenvectors corresponding to k minus 1 distinct eigenvalues are linearly independent. Therefore, that underlined equation there can only hold if the coefficients are all 0. Okay, but how could all those products be 0? Remember that lambda 1 through lambda k were distinct eigenvalues, right? So those differences here can never be 0. So the only way in which all those things would be 0 is if the first k minus 1 coefficients will be 0. So a1 equals a2 equals ak minus 1 equals 0. Well, there is one left, right? AK from the original linear combination, but that will leave us with just this, right? I'm talking about this combination here, right? If all the coefficients up to k minus 1 are 0, then that leaves us with AK, VK, 0. VK, remember, is an eigenvector, cannot be 0. So its coefficient must be 0. So all of them are 0. So that's exactly what we needed to show. And so basically, any set containing k eigenvectors corresponding to distinct eigenvalues will be an independent set, and that will be a key technical result, let's say, in this section. Okay, as a corollary, it's something really useful in applications, this one here. So let's say you have a linear operator on an n-dimensional vector space that has n distinct eigenvalues. Then T is automatically diagonalizable, so V has a basis of eigenvectors for T. So let's say lambda 1 through lambda n are all the eigenvalues of T which are distinct. So then we choose an eigenvector for each. But then again, according to the previous theorem, because lambda 1 through lambda n were distinct, so the theorem above implies that this set is independent. All right, but it is going to be a set of n linearly independent vectors in our vector space V, which is n-dimensional, right? Therefore, it has to be a basis. Okay, so in conclusion, V has a basis of eigenvectors for T, which makes T diagonalizable. Okay, so for example, let's look at the following matrix. We want to know if it is diagonalizable or not. So we look at its eigenvalues. So we compute the determinant of A minus T identity. So 1 minus T, 0, 1, 2, 3 minus T, 1, 1, 0, 2 minus T. And I have it here. It ends up being this. 1 minus T times 2 minus T times 3 minus T. So it has 3 distinct eigenvalues. So A is diagonalizable. So that's pretty much the nicest thing that can happen, right? When you have a transformation or a matrix with distinct eigenvalues, it's automatically diagonalizable. Okay, so then it's natural to ask the question, is this thing enough? So is this what describes diagonalizability in general? So in order for a matrix or a transformation to be diagonalizable, does it need to have distinct eigenvalues? And the answer is no. This is not an if and only if kind of result. So the converse is false. If a matrix is, or a transformation is diagonalizable. That does not imply that all eigenvalues have to be distinct. And here is an example in this direction, or counter example if you want. T from V to V. V is finite dimensional, dimension n. Just the identity operator, basically. T of x equals x for any x in V. So, is T diagonalizable, first of all? Well, think about it. Just take any basis for V that you want, right? V1 through Vn. And apply T to every entry, to every element of the basis. It will be left unchanged, right? Because it's the identity. But then if you do T of V1 equals V1, that gives you the first column of your matrix of T in that basis, and that first column will be 0, 1, 0, 0, 0, 0, right? Then if you do T of V2 equals V2, so the second column is 0, 1, 0, 0, 0. Then the third one is 0, 0, 1, and so on. So what matrix do we get? Identity matrix, right? So the matrix of T in any basis beta you want, or the basis will just be the identity n by n matrix. So yes, there are bases, right, in which the matrix is diagonal, so therefore T is diagonalizable. However, I claim that the eigenvalues of this operator are not all distinct. So let's look at the eigenvalues of the identity operator. So to find the eigenvalues of T, we have to compute the determinant of the matrix of T in any basis you want, minus T identity, right? F of T, the characteristic polynomial. Okay? But the matrix of T in any basis you want will be the identity matrix. So it's the identity matrix minus T times the identity matrix, and I want to find the determinant of that. That will give us the characteristic. So that will have 1 minus T, right, as every diagonal entry, and 0 everywhere else. So the determinant is just 1 minus T to the power n. Therefore, the identity operator has a single eigenvalue, lambda equals 1. However, we're going to say about this eigenvalue. So, anyways, it doesn't have n distinct eigenvalues, right? That's where we're going with all this. So to show that the converse is false. But we're going to say that it actually has one eigenvalue of multiplicity n because it appears n times, right? It's like n is the power of 1 minus t. So we'll talk more about the multiplicity later. Okay, so basically it's not enough, right? It's not enough to just look at the eigenvalues and see if they're distinct or not. So we have to keep on going. Probably not on this page. Yeah. So here's the direction in which we're going now. So first of all, we're saying that a polynomial, just an arbitrary polynomial with coefficients in f, a field f, is said to split over f if there is a way to factor out the polynomial completely with only scalars from that field. So what does that mean? This one here, for instance, is a polynomial that splits over R or over C if you want. It doesn't matter, right? It just factors out completely or with coefficients in R or with coefficients in C. However, this one here, what's going on with this one? This one here does not split over R, right? Because t squared plus t plus 1 cannot be factored over R. So when f equals R, this polynomial doesn't split. But when f equals C, it still splits. Because it can be further factored, right, with complex numbers. So anyways, any polynomial will split over C, right? If you remember the fundamental theorem of algebra, any polynomial of degree n has n zeros over C. That's not the case over R. Okay, so let's see what we can do with this idea. Again, we can go in one direction. We have the characteristic polynomial of a linear operator which is supposed to be diagonalizable. Okay, so we have a linear transformation or a matrix that is diagonalizable. Then its characteristic polynomial must split. Let's see why. Let's say T goes from V to V. It is a linear transformation. V has dimension n, and T is diagonalizable. So we want to take a look at its characteristic polynomial, so the determinant of the matrix of T in some basis minus T identity. I can choose whatever basis I want, right? But I don't know anything about V, so it makes sense to just choose that basis that makes the matrix diagonal, because I know that such a thing exists since T is diagonalizable. So because T is diagonalizable, there exists beta basis for V such that the matrix of T in the basis beta is diagonal, and it will have on the diagonal the eigenvalues of T. All right, so then the characteristic polynomial, that is the one we need to show its splits, is the determinant of that matrix minus T identity n by n. Okay, so what matrix do we obtain? We just get lambda 1 minus T, lambda 2 minus T, lambda n minus T on the diagonal and 0 everywhere else. But the determinant of a diagonal matrix, right, is just the product of the entries on the diagonal. And we're done, right? Because at this point, we got a polynomial that can be completely factored into n first degree terms over the field F in which we're working. All right, so the characteristic polynomial splits, and we're done with this result. So again, maybe this is enough, right? So maybe, just maybe, if you have a linear transformation or a matrix whose characteristic polynomial splits, then it's automatically diagonalizable, right? So it makes sense to ask this question. However, the converse is still false. In the sense that if the characteristic polynomial of a linear transformation, linear operator T splits, it doesn't necessarily imply that T is diagonalizable. And here's an example in this sense. P from P sub 2 of R into P sub 2 of R. T of polynomial f of x equals its derivative. And let's take beta, the basis, the standard basis. So what we want to show about this transformation is that its characteristic polynomial splits, but it's still not diagonalizable at the same time. Okay. So let's look at its characteristic polynomial first. I'm not going to call it f of t, so I'm just going to say that the characteristic polynomial is the determinant of the matrix of T in any basis beta, like the one above, minus T identity, we're working in dimension 3 here, right? So T times identity 3 by 3. All right, so what do we get here? What is the matrix of T in the basis beta? First, when you apply T to the first vector, which is 1, you take the derivative, you get 0, right? So the first column is 0, 0, 0. Then you apply it to x, you get 1. And you apply it to x squared, you get 2x. 0, 2, 0. So we end up with a determinant of the following matrix: negative t, 1, 0, 0, negative t, 2, 0, 0, negative t. And that is an upper triangular matrix. The determinant of such a thing is always the product of the entries on the diagonal. Okay, so the characteristic polynomial of that operator is negative t cubed splits, right, with 3 zeros there. So it splits over the field, which is R here. But still, the claim is that T is not diagonalizable. Okay, let's look into that. So in order for it to be diagonalizable, the space which is P sub 2 of R should have a basis consisting of eigenvectors for T, right? How do I find the eigenvectors? Well, remember from the previous section that once I have the eigenvalues, all I have to do is to look into the null space of T minus lambda identity to find the eigenvectors. But I only have a single eigenvalue, 0, right? So, the only possible eigenvectors of this operator will be in the null space of T minus 0 identity. So that's just the null space of T after all. So to find the eigenvectors, we actually need to find the null space of T minus 0 identity. So the null space of T. Okay, but that would be those vectors for which T of V equals 0, right? Or if you want in terms of matrices, those vectors A, B, C, such that this will give you the 0 vector. But this means on the left we get B. So B is 0. Then 2C equals 0. And that's it. The two of the variables have to be 0. And A is free when we solve this system. Okay, so the null space of T looks like this. A, 0, 0. Or basically just scalars, right? Because A is the first entry. It stands for the coefficient of the vector 1 in the basis beta. All right. So all the eigenvectors will be in this set here. But in order for T to be diagonalizable, how many independent, linearly independent eigenvectors do I need to find? 3, right? Because P sub 2 has dimension 3. To have a basis of eigenvectors, I need 3 of them. So I would need in here to find 3 linearly independent eigenvectors. in that set, right? But that set has what dimension, that space? 1, right? It just has A times the vector 1, 0, 0. This one has dimension 1. In a space of dimension 1, there is no way I'll find 3 independent vectors, right? Because 3 independent vectors will expand to a basis, and the basis contains 1 element, so it makes no sense. Because that is not possible. T is not diagonalizable, although its characteristic polynomial splits. Okay, so let's keep on going then. So we went over that idea of the eigenvalues being distinct. That implied diagonalizability, but not backwards. Now, the characteristic polynomial splits. If it is diagonalizable, then it must split, but not backwards. Keep going. We get back to that notion, the multiplicity of the eigenvalue, or also called the algebraic multiplicity of an eigenvalue. The algebraic multiplicity of lambda is that k, the largest k, for which t minus lambda to the k is a factor of the characteristic polynomial. So for example, this matrix here, 1, 0, 5, 0, 2, 1, 0, 0, 2, has this one as its characteristic polynomial. So T is going to have two eigenvalues, lambda 1 equals 2 and lambda 2 equals 1. Lambda 1 equals 2 is going to be an eigenvalue of algebraic multiplicity, or, for short, multiplicity 2. And 1 is an eigenvalue of multiplicity 1. So this notion is going to be the key thing that will give us an if and only if kind of result, or a complete description of something being diagonalizable. If I go back to that very first failed example here, right down here, there was clearly a connection with the multiplicity, right? So this operator was diagonalizable. It had a single eigenvalue of multiplicity n, right? So something went wrong over there. So now, let's see what we can do with this. So let's say we have a linear transformation T. So again, we're looking into if and only if conditions for T to be diagonalizable, right? So the first idea is, so I need V to have a basis consisting of eigenvectors, right? So the matrix of T in that basis will be lambda 1, lambda 2 down to lambda n, right? Diagonal. But then I need to have n eigenvalues, right, in order for this to make sense. Distinct or not, but there need to be n of them, right? So it needs to split. We went through that already. It has to split in order for this to make sense. So I'm going to say that T has n eigenvalues, but I'm going to say I'm counting multiplicities here. Like in the example above, right, it has 3 eigenvalues, but counting, each of them as many times as they appear. Okay, so out of those n eigenvalues, I have to come up with n eigenvectors, right, in order for the diagonalizability to make sense. And for each of them, I'm going to look in the corresponding null space of T minus lambda k identity. So let me give that thing a name. E sub lambda, so if lambda is an eigenvalue of T, let's define E sub lambda to be that space where we're looking for eigenvectors corresponding to lambda. So this is called the eigenspace corresponding to lambda. All right, so let's make some remarks here. Let me take two distinct eigenvalues, lambda 1 and lambda 2. I already said they are distinct, so B eigenvalues of T. And I want to see what the connection could be between those two eigenspaces. Right, so I take the eigenspace corresponding to lambda 1 and the eigenspace corresponding to lambda 2. I want to see if there is anything, if they have anything in common. Well, what does that mean? If a vector v is in both, what happens? Well, because it is in E lambda 1, which is the null space of T minus lambda 1 identity, then T of V is lambda 1V. Because it is in E lambda 2 as well, T of V is lambda 2V at the same time. But how can that happen? Well, lambda 1 and lambda 2, we said they are distinct, right? So it can only happen if V is 0. Basically, those two things, eigenspaces, which are subspaces, by the way, and you can easily check this. I mean, you don't even have to check because they are null spaces, and we proved in general that every null space is a subspace, right? So each of them contains at least the 0 vector, but any two of them will only overlap in the 0 vector. Okay, keep going with this. How many vectors or eigenvectors can I find in an eigenspace? Not how many in general, but how many independent. Or basically, what dimension can this eigenspace corresponding to a lambda have? So what dimension does it have? Well, it turns out that if the multiplicity, the algebraic multiplicity of lambda is m, the dimension of E lambda cannot exceed that m. Right? It's going to be between 1 and m. So apparently there seems to be no connection between those two things, but they are definitely connected. So let's say that T is a vector space of dimension n. First of all, this m, which is the multiplicity of lambda, is at most n. Does that make sense? Why? Why should the algebraic multiplicity of an eigenvalue be at most n? Think about a characteristic polynomial. What degree does it have? n, right, the dimension of the space. That characteristic polynomial, when you factor it out, lambda is one of its zeros, right? If it has algebraic multiplicity m, that means lambda minus t to the m will show up in the factored form of the characteristic polynomial. And then maybe there is another polynomial that's multiplied by if t has more eigenvalues other than lambda, right? But f has, we said it has degree n. So that power m there can never exceed the degree of f. So n is less than n. Okay, so we want to show this, that the dimension of E lambda cannot exceed m now, where E lambda is, as we said, the null space of T minus lambda identity. All right, so let's just say it has dimension p. Okay, so let's just take p vectors that form a basis in E lambda. Okay, but E lambda is part of V, right? Everything happens inside V, and this set of P vectors is a linearly independent set, so it's going to expand to a basis for V. V, which has dimension n. So I'm going to need to add n minus p more vectors. Let me call this beta. Okay. What do you think the matrix of T in this basis beta will be? Because from here, so I'm going to use this basis to compute the matrix that I'm going to put into the determinant to find the characteristic polynomial, and that will solve the problem completely here. So I want the matrix of T in this basis beta. Well, if you apply T to V1, what happens? V1 was coming from, V1 is here, right? V1 was part of E lambda. What happens in E lambda? E lambda is this one. T of something in E lambda is lambda times that something. So T of V1 is lambda V1, right? Because it's in the null space here. T minus lambda identity of V1 is 0. That's what null space means, right? So T of V1 minus lambda V1 is 0. So T of V1 is lambda V1. Okay, but that will give us the first column of the matrix, right? So which is going to be lambda 0, 0, 0, 0 all the way down. What's the second column? 0, lambda, and then all the way down with zeros because it corresponds to T of V2, right? Now, how far can I go with this? I see no m so far, so m is not yet connected to this basis, right? All I have is n and p. So I can only go up to p with this kind of idea because p is the last one, right, in E. V sub p is the last one in E sub lambda. So that will give me 0, 0, 0 lambda, where this would be like the p row. Okay. So if I want to look at this corner here of the matrix, that's a p by p corner, which is lambda identity. Identity dimension p. That, only that corner, right? So I'm choosing the first p rows and the first p columns there. Okay, but now I have to keep on going. And once I do t of the next vector, which is here, right? The one that extended to the basis for v, I have no control, right? I don't know how those vectors are chosen. And it doesn't really matter how they are chosen. So what will happen is I'll continue like this. I'll have something here. Again, I have no idea what. Some matrix B. And something there. Some matrix C. Now let's figure out the sizes of these blocks that the matrix is divided into. So I have this P by P here in the corner, which we said it's lambda identity P by P in that corner. Then B, what size does B have? N minus P columns, but still P rows. So B is P by N minus P. And C? N minus P by N minus P, right? And this 0 here is going to be N minus P by P, this 0 matrix that I write here. Okay, so the matrix of T in the basis beta is what is called a block matrix, and it is a diagonal block matrix. It has lambda identity and C on the diagonal and B on top. But again, those letters are not numbers, they are matrices. So let's look now at the determinant of T beta minus T identity n by n. If I keep the block matrix format, what's going to happen when I subtract T from the diagonal only? It's going to be subtracted from this corner here on the left, right? Lambda identity will get T subtracted from each diagonal. So that corner will become lambda minus T identity. I'm not doing anything to this matrix down here. And I'm not doing anything to B, right? And I'm going to subtract also from C. I'm subtracting T identity, we said that's N minus P by N minus P, that corner. Right? So I want to compute the determinant of this matrix. And it might seem strange if you haven't seen this before, but if you have a block matrix like this, upper triangular, then its determinant is determinant of M1 times the determinant of M3, exactly as it would be with numbers. And I want you to look into that. We'll assign this as homework in the next homework. So M1, M2, and M3 are certain sizes, right? M1 and M3 are square matrices, M2 is not. Okay, I'll make this more precise anyway, see in the homework. But let me get back here. So that's the determinant of lambda minus t identity times the determinant of C minus T identity. I have no idea what the second one is, but the first one is pretty easy. It's a diagonal matrix with lambda minus T as each entry on the diagonal, and it has size P by P, so okay, so what are we actually doing here with all this? So this is the characteristic polynomial, right? Of P. And lambda had which multiplicity? Well, it all started here, right? We said that lambda had multiplicity m. If it has multiplicity m, the polynomial has to look like that, lambda minus t to the m. Well, I don't know anything about that c. Maybe further factors would come from that, right? Maybe p is not the same as m, but it cannot exceed m, right? Because this polynomial is the same as lambda minus t to the m times g of t. And m is the algebraic multiplicity, so it's the highest possible integer power of lambda minus t. Okay, that's what defines the algebraic multiplicity. So that power of lambda minus t cannot exceed m. And that's pretty much what we needed, right? P, we started with P being the dimension of E lambda, right? That's what they had to show. All right. So here is the main idea where we're going with all this. It turns out that in order for the operator to be diagonalizable, not only that we need a characteristic polynomial to split, but we need this extremal thing to happen. And that means that every eigenspace for every eigenvalue should have a dimension that is equal to the algebraic multiplicity. Let me just, give you a picture, to make some sense out of this before we go ahead and prove all those results. So imagine having, let's see if I have a specific example here. Let's look at this one. Let's work on this one and see if it's diagonalizable or not and connect it to the multiplicities. So when you compute the determinant of A minus T identity 3 by 3, it will reduce to this. So A has two eigenvalues. Lambda 1 equals 4 and lambda 2 equals 3. The second one has multiplicity 2, algebraic multiplicity 2. And the first one has multiplicity 1. Okay, and I want to know if this matrix is diagonalizable. So that would mean I need to start searching for eigenvectors, right, in each of the corresponding eigenspaces. So lambda 1 equals 4. We'll have E lambda 1 as its corresponding eigenspace. How many eigenvectors can I find in there? How many independent? Because remember, I'm after finding a basis. I don't want to pick a vector and the multiple of it, right? I want to choose independent vectors. Well, what dimension can E lambda 1 have? Using the theorem above and the algebraic multiplicity of lambda 1. 1. It cannot exceed 1 because according to this theorem here, E lambda 1 has a dimension between 1 and 1. That's the multiplicity. So how many vectors can I actually assign from this space into that supposedly existing basis of eigenvectors? 1, right? I can only put one vector from E lambda 1 into my basis, if that basis would exist. I can only choose one. All right. All right, so let me look into the second one then. So the second eigenvalue, lambda 2, has an eigenspace of E lambda 2. Of what dimension? I don't know, right? Multiplicity of lambda 2 is 2, so the theorem above only tells me this, that E lambda 2, depending on the actual matrix, the actual eigenvalue, can have a dimension of 1 or 2, right? Now, what if, through computations, I get that the dimension of E lambda 2 is 1? What will happen? Honestly, I don't want to do the computation, so I just want to make a discussion here of what can happen. So if, let's say, the dimension of E lambda 2 is 1, well, that means I can only choose one vector again, one eigenvector from this space, right, to put into that basis that would tell if my, that would tell my matrix is diagonalizable. So in that case, will my matrix be diagonalizable or not? What do you think? In this case here. So again, to be diagonalizable, how many independent vectors do I need? 3, right? My space in the matrix is 3 by 3, so I need 3 eigenvectors which form a basis, but I can only get one from the first eigenspace and one from the second. Where would I get a third one from? Doesn't make sense, right? So my matrix would not be diagonalizable in this case. Okay, so now let's say that E lambda 2 turns out to have dimension 2. If it has dimension 2, then that means there are 2 independent eigenvectors in there that I can choose. Okay. So I had 1 from E lambda 1 and I have 2 from here, and I want to make the 3 right into that basis that I need, and that will always work. Okay, and that's something that will prove in general, and the matrix A will be diagonalizable in this case. Okay. So this is the case that we want, right? The second one. And what made it so special is the fact that the dimension of E lambda 2 equals the multiplicity of lambda 2, right? It was the extremal possibility there for the dimension of E lambda 2. Okay, so in order to show that this works in general, what do I need? Well, if I go back to first page, what we proved here is that if I choose one eigenvector for each distinct eigenvalues and put them together, the set is independent, right? But I actually need more than that now, because what I want to be able to do is to choose one eigenvalue, not for this one, for this one eigenvalue for lambda 1, and two independent eigenvalues for lambda 2, right? I want to put everything together and still be independent. That's actually more than we proved before, right? So before we show that if I choose one for each and put them together, they're independent. Now I want to choose a couple for each and create the basis, right? So that's something that needs to be proved. And it is true. So here it is. So you have a linear operator, you have k distinct eigenvalues, lambda 1 to lambda k. And then for each lambda, you choose a finite linearly independent subspace of E lambda I, right? So you just choose a couple vectors independent in the eigenspace of lambda I. And then you just put everything together into a single set called S. You want to show that S is still independent. That's exactly what we need, right? That allows us to choose as many independent vectors as we want from each eigenspace. Okay. Let me give some names to those vectors. So Si is Vi1, Vi2, Vi, well, I don't know how many vectors. I'm allowed to choose as many as I want, right? So now the second index here must depend on I as well. The I and I. Right, so let's say that for the first one I'm choosing 3 vectors, for the second I can choose 5, right? Every time I can choose different things. So then S is the set of vectors Vij with I between 1 and k, and every j is between 1 and ni. All right, so this set, I want it to be linearly independent, so I'm going to set up a linear combination equal to 0. I have 2 indices, so I'm going to sum over both I from 1 to k and j from 1 to n sub I. And then Aij Vij equals 0. I want to show that all those coefficients must be 0. Okay, but now if I'm looking at this sum and putting some parentheses here, when I'm summing over j, I'm actually summing inside Si, right, inside a single set. So this sum here is a linear combination of vectors in Si. Si is part of the vector space E lambda I. which is closed under linear combinations. So this sum becomes a vector in E sub lambda I. Okay? Because all those vectors, the ij when I is fixed, will belong to E lambda I, which is closed for, on the linear combination, so I'm in there. So basically what this means is that I have a sum of, no, I'm not going to write it again actually. I have one vector from E lambda 1 plus a vector from E lambda 2 plus a vector from E lambda 2 and so on equal to 0. Okay, but now let me go back to the first page and that first result that we proved. Okay, so I'll go back here. This first theorem said exactly this, that if I choose one eigenvector for every distinct eigenvalue, the set will be independent. I have one eigenvector for every distinct eigenvalue, and I have a sum equal to 0. Right? That cannot happen in an independent set. But maybe V1 through Vk are not really eigenvectors because they are vectors in E lambda, right? E lambda, E lambda is defined to be the set of eigenvectors, but it also contains the 0 vector. It's a subspace. Remember that eigenvectors are not allowed to be 0. But E lambda is a subspace, contains 0. So this can only happen if I'm choosing all of them to be the 0 vector. Otherwise, they are independent if they are eigenvectors. According to theorem, I think it was called 5.5. The one on the first page. Okay, but if each of them is 0, then each of those sums is 0. Take one of them, sum j equals 1 to ni, aij, bij equals 0. Okay, but now I'm doing this inside this set. I mean, it's a linear combination with entries from the set Si, and Si is, by assumption, linearly independent. That automatically means that the only way to do that is with all 0 coefficients, right? So basically, this theorem, you like it or not, it allows us to do exactly what we need to do, right? It allows us to pick as many independent vectors as we want from every eigenspace. Right? How many will we want? The maximum possible, exactly the multiplicity of the eigenvalue. So we'll put this, we'll combine everything into the final, if and only theorem next time, but we pretty much have all the ingredients now to finalize this. Just stop here.